Hi, everyone. Um, my name is Sujay, and today I'm going to talk to you about Data Mesh at Netflix and how Data Mesh as a platform has democratized stream processing at Netflix. And then we'll go a little bit deeper into how we've evolved it with Streaming SQL. First of all, I'm really happy to be here. I remember I was attending DevOps in Belgium, I think a few years back, and really good to be back as a speaker here. And London is an amazing city, so I'm really glad to be here and exploring the city as well. I think people are still trickling in, but I'll kind of get started. Um, so yeah, that's what the talk is about. A little bit about me. I'm a software engineer at Netflix. I work in the data platform team there, mostly working with Apache Flink and Apache Kafka and Iceberg. So a lot of it is real-time data infrastructure. As you can imagine, at Netflix, we do get a lot of real-time data, and we need to make decisions pretty quickly with the data that's coming in. And that's something that I focus on here at Netflix. Earlier, I was at Meta, Facebook, as it was known back then. I was part of the data platform team there as well, working on Presto, which is like a distributed compute engine as well, more on the batch side. And before Meta, I was at Microsoft. At Microsoft, I was doing more general distributed systems, large-scale distributed systems. I was part of Microsoft Azure in the very initial days. And also worked on messaging services and messaging systems. They're pretty enriching experience. In general, I'm very interested in data platforms, making data accessible to be able to make decisions out of data. Distributed systems is also something that I'm quite interested in. I've worked in it in the past. And of late, as there's more and more machine learning and the value of data is more apparent and more clear, I'm also focusing a little bit on how we can leverage data for real-time machine learning and improving outcomes in ML and AI in general. Are you guys able to hear me well? My throat is a little off, so sorry about that. All right, so what are we going to talk about today? We will first give an overview of stream processing. What is stream processing? Why is it used? And then we'll go into how we do stream processing at Netflix. Then we'll talk a little bit about Data Mesh, what it does as a platform. Go a little bit deeper into Data Mesh architecture and how it's built, and talk about Streaming SQL, which is a new addition to Data Mesh. And then eventually we'll talk about how we handle the operations for a platform like this and what has been our learning. So to start off, Netflix, we are present in over 190 countries, and we have over 300 million members. And all of our members are using over 1 billion devices to log into Netflix to watch their favorite shows and movies. And as you can imagine, with this kind of scale and this geographic distribution, there's unique technical challenges that we have to deal with. And today, of course, there's a lot that powers the Netflix experience, but today we're going to dive deeper into some of the data processing that happens to provide the Netflix experience. So let's talk about stream processing. How many of you are familiar with stream processing or have heard about it? So stream processing is basically the processing of data in motion. That means that we are performing computations on data as it's being produced or received. And this paradigm of computation is usually associated with real-time data. So as you can imagine, for Netflix, for example, as a user is browsing the Netflix home screen, they're making clicks, or they're reading about the shows that they're interested in, all of it is generating a lot of events that can then be leveraged to make decisions in the background on what could the user be interested in and how do we improve the recommendations that we show to them, right? So stream processing is a little different from like the batch processing. Batch processing is the more traditional way of data processing. There's a lot of differences, but one fundamental difference is that in stream processing, you model your data as an unbounded stream. which means that your data has a start, however, it does not have an end. Whereas in batch processing, your data would have a start as well as an end. So there's a well-defined start and end. And this has some implications on how you reason about like the completeness of the data, how do you process the data in a particular order? How do you, in stream processing, there's this notion of time semantics and what kind of time do you use to process the events, which are unique a little bit to stream processing. And your data doesn't really have an end, so it's like continuously being processed. Typically, if you're looking for more real-time insights, like if you want to make decisions quickly on the data, that's when you would leverage stream processing. And if you have event-driven applications, that's another big use case for stream processing. So at a very high level, there's two broad categories for stream processing. One of it is change data capture. Change data capture is a process of identifying and capturing changes that happen in a source database, and then in real time or near real time, transmitting those changes down to another system. So let's say you have an operational data store like MySQL database or Cassandra, and then you want to replicate the changes that are happening in that data store, which is your online data store, to, let's say, your data warehouse. That would be something that falls in change data capture. At Netflix, our operational data stores are our system of record for a lot of our critical entities like movies and talent and profiles, etc. So it is often very critical for us to always maintain an up-to-date, fresh copy of that data in our downstream systems, because then the decisions that are being made can be made on the freshest data and not like on a stale version of the data. So for example, if a movie changes, yeah, go ahead. It depends, but we try to be as near real time as possible. How much ever the system allows, and every situation can have its own accepted lateness. But the goal is always to be within, let's say, seconds, if not milliseconds. In change data capture, there's, of course, you could replicate the data store as it is from source to destination. But then you may also want to do some transformations in between. Sometimes you're getting the change feeds from your source, but you may want to do some filter, projection, rename certain fields, massage the data in some way before you land it to the data stores. You could also do complex transformations like windowing or aggregations or join multiple streams together. And all of it can be powered by stream processing. The other large bucket is just data that's produced by microservices. So as you can see, there's a lot of services and applications at Netflix. And all of these services are producing a lot of data. A lot of that data is pretty valuable, and we want to make sense of it as much as possible. So all of this data needs to be processed and transported to a place where it can be analyzed. And again, that's where some of the stream processing can be used. So at a very high level, you have change data capture, from data store to data warehouse. And then you have, we call this event streaming, data that's produced by applications. And then you're doing some processing on top of it and landing the data somewhere. So that's the overview of stream processing. Now, let's go into how we do stream processing at Netflix. So at Netflix, we primarily rely on two fundamental building blocks to do stream processing. We use Apache Flink and Apache Kafka. Apache Flink is an open source distributed compute engine. Like, it's used heavily for stream processing and also for batch processing. And Kafka is it's like a distributed messaging system. It's the de facto standard, I think, in the industry. Very, very popular as a message queue and used for stream processing. Both of these technologies are actually quite popular in real-time data processing world. So with these engines, we expose to our users within Netflix two different ways of doing stream processing. Right? The first way would be to write your own Flink job. And this is meant for more power users, right? Like we have an internal platform in Netflix called Stream Processing as a Service, which can be used by users to write their own Flink jobs. Typically, they would be writing their job in Java or Scala, and they would use Flink's native DataStream APIs to build their application. Very powerful. However, it also means it has a little bit of a learning curve. You need to understand the streaming ecosystem. And then we have Data Mesh, which is an abstraction on top of the Flink and the Kafka platforms. And the idea here is that Data Mesh gives you higher level building blocks for someone who may not be as familiar with stream processing to still be able to come in and sort of build their streaming pipelines without needing to understand the lower level details of how streaming works. And then in Data Mesh, we provide some fundamental building blocks. One of the powerful ones that we've added is SQL, where you could express. SQL is very flexible, right? So you can express your transformation in a very flexible way. We'll go deeper into that. So let's talk about both of these things. So there is the lower level SPAS platform, which allows you to build custom Flink jobs. And the advantage here is that you're building your own Java or Scala application using the DataStream APIs. You have access to pretty low-level primitives. You can manage the state. You have access to timers. And it can be very powerful if you know what you're doing and if you're already an expert in that field. However, it does have a steep learning curve. Like, to be able to build your own Flink job, you need to understand the streaming ecosystem. You need to understand how the connectors behave. What does it mean to have state in a Flink job? How do time semantics work? What is the meaning of watermarks, etc. So while very powerful, it can be hard for someone who just wants to come in and solve a business problem. For them to really get into the nitty-gritty of the streaming ecosystem. That's what inspired Data Mesh. And with Data Mesh, the problem that we're trying to solve is, how do we bring all of these capabilities that come with a streaming ecosystem, streaming platform, and then make it available to users who may not be very familiar with the streaming technologies, right? At a very high level, Netflix, we're processing over 14 trillion records on a daily basis. So that's a lot of data. And then to have bespoke streaming pipelines or bespoke apps processing all of this data can become quite complex quite quickly. And that's where the need for creating a managed platform which standardized some of the most common patterns and made it accessible to more of our users. That's where the value proposition for Data Mesh really comes in. So it takes away a lot of the complexity away from our users, giving them basically lowering the barrier to entry for someone who wants to use stream processing. And yeah, it gives a fairly unified approach for someone who wants to build streaming pipelines. So yeah, we've talked about for stream processing, we use Flink and Kafka. And then at Netflix, we have two levels of doing this. We can write our own Flink job, or we can use the Data Mesh platform. Now let's go a little bit into what are the building blocks for the Data Mesh platform. Now this is a data streaming pipeline represented as a block diagram. What you have is, you have on the left-hand side, you have a source, which is what's receiving the incoming data. Then you have some sort of transformation happening. As the events are flowing in, you may be doing some filtering out certain events, you may be doing some projection, you may be doing some aggregations. And then you would typically be sending that data over to either another data store, your warehouse maybe, or you could be sending them down to other consumers who may be interested in certain pieces of this data. Right? So this is typically a pipeline. And then taking a step back, for Data Mesh, we have the Data Mesh control plane, which provisions and manages these pipelines. The Data Mesh control plane leverages on our Kafka control plane and our Flink control plane. That's stream processing as a service and Kafka as a service platforms. And then completing the picture, you basically have producers on the left-hand side. So these could be anything that's producing data. Like we talked about in case of change data capture, this could be a data store, change feeds from a data store, or it could be a microservice, which is generating data, or it could be another Flink job, which is producing data in a streaming fashion, right? And the data comes in to a data mesh pipeline, it gets processed, and then the data is written to the destinations. And there could be many destinations as well. So we at Netflix, we heavily use Apache Iceberg, which is a very common destination. Elasticsearch is heavily used as well. And then if you have further consumers who want to consume this data in a real-time fashion as well, they could be, you could write the data down to a Kafka, another Kafka topic, and then you could have further Flink jobs or apps that consume from that Kafka topic in a real-time manner. So this kind of is like the ecosystem of where data mesh fits in. The part in the middle is the data mesh, the pipeline, and then the producers and consumers are also part of the ecosystem that we provide. So let's dive a little bit deeper into what all of these different components mean. So at a very high level, data mesh has three fundamental pieces. There's the source, the data mesh source. A data mesh source is essentially where the data is coming in. And these sources can be backed by a CDC source connector. So it could be like MySQL or Postgres, or CockroachDB is another one that we use, where we're listening to the change feeds from these source databases. Or it could simply be a Kafka topic to which an application is producing data. So this is the data mesh source. Then you have the data mesh transforms. And here, the platform provides a couple of sort of options for users to be able to transform their data. The first one is the SQL transform, which where you could come in and write your SQL query, and that gives you the power to change your data the way you want. Or we also have a GraphQL processor, which allows you to enrich your data via a DGS, via a GraphQL query, and you can transform it that way. By the way, in data mesh, if these are the two processors that are provided by the platform, basically, that we build and give to our users. But if this doesn't satisfy your need and you have a use case which needs a custom solution, you do have the capability to build a custom data mesh processor as well. And that's something that can be maintained by our team. But we provide that flexibility to our users. So you have the source, transform, and then you have the sinks. And the sink is where the data is landing. So these are processors which are basically going to write the data to the external destination data stores. The commonly used ones at Netflix are Elasticsearch, Iceberg, Kafka. And then we are working on a Druid sink. And Druid is used for real-time analytics. So that's something that we're exploring right now. The sources, think of it as basically these are backed by a Kafka topic. And all of these processors, the transformation processors, as well as the sync processors, are Flink jobs. And this is what a data mesh pipeline would look like. You have on the left-hand side, you have the source. I don't know if it's readable, but it's called play events POC. But basically, you can name your source, but that's where the data is coming in. There must be some application which is writing to this in a streaming fashion. Imagine the Netflix client is sending events as the user is browsing or playing movies. Then in the center, the playback enriched. This is a SQL processor, which if we open this, it would have a SQL query inside of it, which just by the name, it says that it's probably enriching the data. So maybe it's calling an external data store to hydrate some of the details of the stream coming in. And then that data is landing into Apache Iceberg and Apache Druid, like an Iceberg table, which can then be used by other teams or some batch jobs to sort of process that data further down. And the Druid sync can be used for more real-time analytics and observability. OK, so what happened? So SQL, in this pipeline, you already see that SQL is there. This is the SQL processor. But when Data Mesh started, we did not really have a SQL processor. We had the sources, and then we had the sinks. And then if anybody wanted to do something custom, they would either have to build their own Data Mesh processor, or they would write a custom Flink job. Remember that we talked about earlier, which is a pretty it has a steep learning curve. And what we started realizing over time was that more and more users had the need to do transformations on the data, but then it was becoming a pretty heavy lift to have to write their own custom data mesh processor or to write their own Flink job, because they needed to understand the details of streaming ecosystem before being able to be very productive with that. And that's where the need for SQL came in. SQL is a very standard way of working with data in the industry. And the idea is that you can come in and write your business logic without really needing to understand the nitty-gritties of the streaming ecosystem, or how the DataStream API works, and how do I manage my state, and what does it mean to how do time semantics work. So we kind of abstract that away from the users as much as possible. With SQL, so let's spend some time on this GIF, but basically this is how the SQL processor works. What you see here is that you're writing the query. And so one of the things we wanted to do with SQL was to give users a very quick feedback loop, because SQL queries can be fairly complex, right? And for it to be effective, we wanted a way for the users to be able to quickly write their query, but also run their query. So what's happening here is, so let's follow here. So you have a pipeline, you write the SQL query here, your query is being validated, and you're getting feedback on whether this is valid or not. It's doing some kind of a join. And then you have this option to run the query, where we are sampling data in real time from the source topic, executing the query, and giving the user the immediate result on what your query is going to look like. So the idea is that you can iterate on the query as much as you want, get this feedback, right? And then once you're satisfied with the results, then at that point, at this point, the Flink job has not been provisioned yet. We've created an ephemeral Flink cluster for you to run the query. But then once you're satisfied with your query, you can then basically go and deploy the pipeline and deploy the Flink job, which would then provision the actual underlying resources. So let's talk about the architecture. You saw the flow of what was happening. That's kind of what is being described here as well. So the first thing is that the user would come in. They have this query box, right? And they would write their SQL query here. Because we wanted quick feedback for the users, and SQL, again, is free-flowing text, so you could make a lot of mistakes, right? We do have automatic validation on the query. So as the user is typing the query, every few seconds, we are firing off some validation to kind of give feedback to the user that, hey, the column name that you typed doesn't really exist, or this syntax doesn't exist. And we also have in Data Mesh, and I'm going to go into this a little bit more in a couple of slides, but we have schema defined at every hop in the pipeline. And schema is a pretty important part of Data Mesh. So another thing that we do in real time is we validate the query, but we also infer the output schema, right? So let's say if you're projecting 2 fields in the SQL query, your output schema will only have those 2 fields. But then if you change it to project 3 fields or 4 fields, or rename the fields, your output schema would now have to match your updated query. So as users are typing the query, we are validating it, but we are also inferring what the output schema should look like based on that query. And this keeps happening interactively. Then the user iterates on their query. Once they've constructed a basic query, then at that point, they can basically use the run functionality to run their query. At that point, what happens is that we submit that to an ephemeral job, which is essentially a Flink session cluster. This is like a multi-tenant Flink cluster, which we don't use for running production jobs, but it can be a very lightweight environment to be able to run queries without taking the overhead of startup time and stuff like that. Think of it as like your computer, which is always on. You can come in and browse do some things without needing to start and stop and all of that. So it's great for sampling and giving feedback to the users quickly. Okay, so what happens in the ephemeral job is this Flink job is going to run the query that's submitted by the user. And then we use another real-time compute engine that's built by Netflix as well. It's called Mantis. This is open source as well. This Flink job is going to write the data, the output data, to a Mantis sink, which then the browser can basically pull from. And that's how what you saw in the previous slide. When we do this run query and the data comes in, right? That's kind of what's happening. We're submitting the job to a Flink session cluster. The Flink job is writing the data to a Mantis sink, and the browser is then pulling data from the Mantis sink, like in a streaming fashion, and that's what's basically populating this data here. And then the idea is that the user can go through this loop a few times, finalize their query. Once they finalize the query, they can save the query, and once they save the query, that's when a long-running Flink job actually gets deployed. Like, to compare it and contrast it with what would have happened earlier, without the SQL processor, you would have to basically create your own Java project. You would have to basically build your own sort of application to do the same thing using the DataStream APIs, which can be very powerful, but also more time-consuming compared to just writing a SQL query. OK, so like I mentioned, one of the things we wanted to do with the SQL processor was to give users a very quick feedback to make it sort of more powerful. And what we did for that was we basically created a utility, which is creating a very minimal Flink environment to be able to validate the SQL queries that are being written. So without necessarily taking the overhead of a full Flink environment, we took only the essential components which can parse, validate, and analyze the queries that are being written, and basically to give quick feedback to the users. And this is very powerful because this has cut down the feedback time pretty dramatically, like I showed in the previous diagram, where we are firing off a validation and a schema inference every 30 seconds. It happens behind the scenes. It's using this embedded Flink planner, which is pretty lightweight and it can quickly validate the queries. And what we are also doing is we take the query. So this planner takes the query, it parses the query, and then traverses the calcite tree for that SQL query. And we have a notion of allowed operations in SQL. So because SQL can be pretty powerful, but also people can do a lot of crazy stuff in SQL. As we release the SQL processor, we wanted to put some guardrails on what are the things that you can do and what are the things that you cannot do. Like, as we got confidence on the operations that we can support, we could open it up. So this calcite tree analysis really helps us having a well-defined list of operations that we allow, that we are confident in running, and blocking things that we're not supporting at this moment. And then it's zero execution validation. We've kind of decoupled the query validation from the actual execution. Execution is resource intensive, but validation can be quick, and that's where a lot of the value is. And then it has dramatically improved the developer experience because you're getting quick feedback on your queries. So since we released the SQL processor at Netflix, we've seen rapid growth and rapid adoption. Basically, within a year or so, we've had more than 1,200 deployments of these Flink jobs, which is pretty great, and it clearly shows how it's providing value to our users. And then, I showed you a simple data mesh pipeline earlier, which was just a source, processor, and two sinks. But then you could do things like this as well, right? Here, you have the source in the left, and then you have all of these processors doing different kinds of processing and transformation. So you see a lot of SQL processors as well as I think there's some GraphQL processors, right? And data mesh allows you to be able to do fairly complex things. And the beauty is that a lot of these processors can, the architecture is allows composability. So if you wanted to, let's say, if you realize that the output of one of these is something that could be beneficial to another team, you could make that a discoverable output, meaning that somebody else in a different pipeline could consume data from that point on. OK, so we talked about SQL. We talked about data mesh pipelines, the building blocks, the source, the processors, the sinks. Right? Let's go a little bit deeper into the underlying layers. So what you saw in the pipeline view was you saw the data mesh source, you saw the processor in between, and then you saw the sinks. What's happening under the hood is that this logical DAG that you see in the UI actually corresponds to a physical DAG down in the physical layer. And basically, the data mesh source is essentially a Kafka topic, right? Then you have the SQL processor, which is a Flink job. And then the SQL processor is then outputting its data, its whatever processing it has done, to another Kafka topic, which is the output of that SQL processor. And that becomes the input to the downstream sinks that we saw. So the Iceberg sync processor and the Kafka sync processor. And these are Flink jobs which are then writing to the Iceberg table and the further down Kafka topic. And going one more step further, there is schema at every hop. So not only do you have the Kafka topics in between and the Flink jobs, but then at every hop, basically the producer has its schema that it needs to produce the events with. And then the SQL, that becomes the input schema for the SQL processor. The SQL processor transforms the data, and then based on the transformation, based on the query, it would have an output schema, because the input schema or the shape of the data coming in could be different from the shape of the data going out. So there's an output schema there, and then that becomes the input schema to the processors further down. So there's the Kafka topics, and there's the schema at every hop, basically. OK, so let's talk a little bit about schema. Schema is fairly important as well as quite complex. And it's a very fundamental building block for data mesh in data mesh. So we require either definition or inferring of schema at every hop. So the producer has to have a schema, the processors have to have a schema, and the sink also has to have a schema. And we utilize a centralized schema registry to be able to do all of this. Our schemas are in Avro as of now. And basically this registration and definition of schema at every hop allows the platform to then reliably enforce and propagate any schema changes that happen. So for example, if you have a schema that gets updated, we can use this view to see. So if the output schema here was to get updated, then the platform, because it knows the definition of schema at every hop, it can first do a compatibility check to check, hey, if the schema changed, did it change in a way that we support? Is it compatible? And then if it is, then it can propagate the schema change down through each of these hops, all the way to the Iceberg table and to the Kafka sink. And that's very powerful. Like data mesh supports automatic schema evolution, which means that if you change your schema in a compatible way at the source, it will be propagated down, all the way down, even through that crazy complex pipeline that we saw. schema will get updated through all of it. And we've built a fairly sophisticated ecosystem around schema. So we have the ability to edit schema. We have a schema editor. We've built Gradle plugins for our users to be able to register and update their schemas. But also we have a dedicated schema control plane, which handles this compatibility check as well as propagation of the schema down. And at the end of the day, schema benefits everybody in the ecosystem. Like, it benefits the producers because they have they have the ability to change the schema as the data changes. So it's very adaptable, and they have the ability to sort of edit the schema as well. It gives a very consistent view to the consumers of the data. It's guaranteed that, hey, if this is the schema, this is how you can expect the data to arrive in, and you wouldn't have some craziness in the data. And it's great for the platform as well, because then we have a very well-defined contract to follow with the producers and consumers, right? And it kind of decouples all of these different pieces, which makes it more powerful. So yeah, that's some details on the schema. Just to give you a sense of all the different kinds of schemas that are playing a role in the data mesh ecosystem, even for a single Kafka topic, right? Internally we track 3 versions of schema. One is the producer schema, which is what the producer is producing the data with, and as you can imagine, it can change over time, right? Because the needs change. We have the notion of a reader schema, which is essentially the schema that this Kafka topic, every message in this Kafka topic can be represented going back in time. So it's kind of like a union of all the previous versions of schema. And then there's the consumer schema, which is basically what different consumers are interested in. This may not necessarily match the schema of the producer. OK, so all right. Data mesh also, initially we started as our users mostly use it's a platform, but our users use the UI to build data mesh, right, by dragging and dropping all of these building blocks and the processors. But over time, we started realizing there was a need for people to be able to define data mesh pipelines in code. And we also have that capability where you could define your pipeline as a YAML and basically manage it from there. And you can manage your schema also from there. Yeah. It does matter, yeah. And we have some rules on how we handle the compatibility, but we can discuss more. Yeah. I'll skip over this. In the interest of time, I want to cover some use cases, but at a very high level, we provide a lot of building blocks, a lot of goodness to the users already. One thing I want to highlight is just the rich connected ecosystem, right? Because as data mesh platform integrates more source and sync connectors, it becomes more and more powerful for our users, right? They can talk to multiple systems using the same platform. So, and then we have things like auto scaling, which means that the platform can scale up and down as the incoming data increases or decreases. OK, so let's talk a little bit about the use cases that use data mesh. So one is personalization. Netflix, our mission is to entertain the world, and then everybody has different tastes. So we try our best to recommend to people things that they would be interested in. A lot of the personalization at Netflix uses this infrastructure of Flink, Kafka, and data mesh. Typically, every user activity that's happening on the Netflix UI is passing through these platforms, and then we're making sense of what could be the best thing to recommend. And this influences the rows that you see on your Netflix app, even the art that you see for each of the titles, and things like that. Set detection. This is also a very common scenario where data mesh and our streaming ecosystem is used basically in real time to capture logs from all of these different sources, like Google Drive or anywhere else that our security team wants to monitor, and then using data mesh pipelines to land this data either to Iceberg or to Druid so that it can be used for threat analysis and run some detection algorithms. Games. Netflix recently invested in games, so it's a newer division within Netflix, and we are seeing data mesh being used heavily to build like a games analytics platform. And the idea behind it is that as new games onboard onto data mesh, and even for existing games, we make it very easy for someone to instrument the game with new types of events. And if a new event is added, programmatically create a data mesh pipeline corresponding to that event and land the data about that event to, let's say, Iceberg or Druid to be able to do real-time analytics. These are some examples of where data mesh as well as like the streaming ecosystem is used. Quickly going over the scale of data mesh, we're processing at peak over 100 million events per second. And that translates to 8 trillion events every day. And then we have a pretty high number of pipelines and Flink jobs and the Kafka topics. And it's been growing, it's been growing pretty rapidly, so there's a lot of value that it's providing to our users. So as you can imagine, with such a high scale, the operations can become very challenging, right? We are a very lean team of a few engineers who are managing this platform. So for us, the key for operating such a large platform is automation. We've tried to, and we constantly keep trying to invest in automation as much as possible, because it's with these many jobs and Kafka topics, something is failing all the time somewhere, right? And it's going to be crazy if we get paged for every little thing. So yeah, so we've invested in automation. One big thing is auto scaling, which means streaming traffic does not have it doesn't have a constant throughput at which the traffic comes in. There's peaks and troughs, and US time has different peaks, and Europe may have a different peak, and Asia may have a different peak. So autoscaling is quite important, and what it does is, as the shape of the data coming in changes, as the throughput changes, volume changes, we adjust our infrastructure to scale up and down along with it. Another thing we've invested in is, of course, we have alerts for all of these Flink jobs and pipelines so that they're running, they're healthy. But then, at the same time, a lot of the times, there are standard patterns that can be followed for remediating the known issues, right? And we've invested in automated remediation, which means that depending on the signals or the faults that we see in the system, in the pipelines, the first responder can be a computer. It can be another service. It doesn't have to be the on-call, which takes away a lot of the on-call load from us. So things like, if there's high latency, if the job health is bad, we try and remediate it first, quickly, automatically, before paging the on-call. And then we've also, schema is fairly complex as well. So we've built a lot of tooling around schema and how schema evolves and what rules are followed for schema changes and what is allowed and what is not allowed. Because we are running so many Flink jobs, we also need a way to do fleet management, which means that all of these jobs need to be upgraded if there's a new version of Flink or new version of Java and stuff like that. So we've invested a lot in all of these different tooling capabilities. This is an example of the automatic remediation that I was talking about. So in this pipeline, this is brand new, by the way, that some of my teammates have built. So this particular processor in the pipeline is in a red state, which means that it has some fault going on. And what our fault management system does is, first it tries to figure out, okay, what are the failures that it's seeing in the job, right? So there are failures around like check. So it's telling us that the Flink checkpoints have been failing for a while, and some Flink tasks have been failing. It tries to have some description of what the problem might be. This already takes a lot of the burden away from somebody. If let's say if I got paged for this processor, then I can come here and quickly see, okay, a summary of what all is going wrong, and then figure out, okay, what actions do I need to take to fix it. This is the first step. In a lot of cases, it will also attempt a remediation by itself. And if that doesn't work, then it would page us. In a streaming platform, it's quite important to react quickly to faults because the whole value proposition of streaming is to land the data quickly to our users. So we don't want delays happening in the system. And finally, of course, it's been a long journey, but we've learned a lot, and very fruitful journey as well. I think the main takeaway that we've had is having higher level abstractions that take away some of the complexity of the underlying systems is extremely valuable for productivity. Just with the growth of data mesh, you can see that a lot of the people who may not have been able to access the Flink and the Kafka ecosystem just because of its complexity are now able to utilize it because it's made so simple for them, right? These abstractions lower the barrier to entry, which means that more and more people can use it to solve like different business problems. We've also adopted an approach of working closely with customers. Basically, rather than waiting to release a product when it's perfect and 100% done, we try to engage with some alpha or beta customers early on so that we can kind of iterate with them as we build the product, and that gives us very useful feedback actually, because we can spend all the time in designing and building the perfect product, but until you put it in the hands of someone who actually needs to use it, I feel like that's where we get a lot of the useful feedback. And then we focused a lot on the user experience and guardrails. I think guardrails are extremely important, especially with SQL. That was our biggest fear, that it's okay to run templatized Flink jobs which do one specific thing, but SQL was different in the sense that now you have a text box where people could just write very, very complex things, and how that would, what kind of operational load that would cause is something that we were a little worried about. So we invested heavily in the guardrails, the calcite tree parsing that I talked about, allowing only certain operations, giving quick feedback. All of that helped in keeping our operational burden low with the SQL processor. But yeah, basically those are our learnings, and that's it. Thank you for attending. I think I'm almost on time. Yeah. Thank you. Go ahead.
What's the relationship of the SQL version here compared to Flink SQL?
It's basically Flink SQL. Yeah, we are under the hood. We are running Flink SQL, and that's exactly the semantics and the syntax and everything that we follow. Yeah, yeah.
It's about all the scaling, because how do you scale the task sorts for the Flink? How is that achieved?
Yeah, so actually we have two ways of auto-scaling right now. Like one, the Flink open source also provides auto-scaling, which is fairly recent. That we are in the process of evaluating and adopting it in our system. But the way we had built an autoscaler even before Flink came up with an autoscaler, because we had a lot of jobs already that we had to manage. And the way that works is it basically keeps an eye on certain key metrics like the CPU utilization, the memory utilization, the lag. Lag is a big metric, like the consumer lag for the Kafka topic, for the Flink job. And it does some calculations to figure out if the lag is increasing at a rate where it may not be able to sustain, there may be delays to the downstream data. So then it would just scale up the number of task managers. And the way we scale is we increase the number of task managers for the Flink job. Yeah. Yeah.
You've got all these schemas, right?
Yeah.
These different things and they're transformed. Is there some sort of catalog or marketplace for your users?
Yes, we do have a schema registry. I don't know, I think we can do a better job at bringing it up and making the discovery easier, but we do have one centralized schema registry where everything is registered. Yes. Yeah. The message itself does have that schema ID associated with it. And then how do we deal with incompatibility? It's a very interesting question, but also a very detailed one, because there are certain things that we allow within that we can handle within data mesh gracefully. Like, for example, certain changes like deleting a field or adding a new field is handled gracefully, because because of the notion of the reader schema and the consumer schema, we can do some things there which doesn't break the downstream consumers. So we evolve the schema in a compatible way. However, there are certain things, like, for example, if you change the type of a field from from string to float or something like that, that would count as a breaking change. And in that case, we do have certain steps to follow. Like, we would typically block that and then require the user to either recreate the pipeline or work with the consumers to kind of propagate it all the way through, because we don't want to break the consumers. But it's fairly complex, and there's a lot of use cases. There's a lot of edge cases that we have to think about there. Yeah, go ahead. Yeah, great question. Okay, so sorry, I'm not repeating the questions actually. So the question is, how do we deal with upgrades, and that we don't break the pipelines? Yeah, that's something that we are still learning, especially as our fleet has grown a lot. But we we first upgrade the processors in certain pipelines, like canaries. We use canaries a lot to basically validate the upgrade to some extent, and then you do a lot of testing around it for the situations that we can think of, like data loss, and give it to a high throughput stream and stuff like that. And then that's the first level, right? And the second level is actually to also make sure that the rollout doesn't happen all in one go. We do a very slow phased rollout to make sure that if something does go wrong, we catch it early and we limit the blast radius. Yeah. Not always. Like, depends. It depends on how you're consuming that data. If your goal is really to just send it to Iceberg, right? You can send it to Iceberg, and there you could be using it. It may even be some other team, really, who needs to process that data, or you could be using batch processing from then on to process the data. You don't need to know the internals of streaming at that point, right? The SQL. Mm-hmm. I see. The user. Yeah, yeah. In the most complex SQL, yes, they would need to know, like, if they are doing some kind of window aggregation and they need to use time semantics and stuff like that, they may need to know some of those details. We can't abstract all of that away. But for simple things like, hey, I just want to rename my field, I want to filter out certain fields, it's very simple, basic SQL, which they don't need to think about, like the streaming details there. So yeah, there's two levels there. But so far, our experience has been that the users, because of the interactive capability that we've provided, users have been able to write very complex SQL that even I would not be able to come up with, and they've just been able to do it. So we see these processes running in production right now.
So you talked about the calcite tree analysis and the going to information data.
Yeah.
Do you also have guardrails? So does that analysis takes care of the cardinality of the fields, like if there are high cardinality fields resulting in high numbers, not just the schema?
Just the schema. We don't, because we don't actually sample the data in that step. We only look at the schema as well as the operations and the expressions. If we don't allow window aggregation, for example, we'd block it there. Yeah. Awesome. Yeah. Go ahead. Yeah, that's a great question. The question is if there's some analysis of what kind of pipelines exist and if they can be merged. We haven't looked into that. I think there's scope for us to do that. But right now, unless you know already that a team has a pipeline that I can just reuse, you could come and reuse it. But the system by itself doesn't do any kind of clubbing pipelines together. How am I on time?
There's a break right after.
Oh, okay. So we should stop now. All right. Thank you. Thank you, everyone.